Hello everybody, and welcome to our video on angles and their measure. So we're going to start out with some basic definitions that'll help us formalize what it means to be an angle. So definition: a ray is a part of a line made up of a point, called an endpoint, and all of the points on one side of the endpoint. So we've got an endpoint, and then we've got the set of all points that are going in one direction from that point. So an angle is formed by rotating a ray about its endpoint. Its initial side is the starting position of the ray, and its terminal side is the final position of the ray after rotation. The endpoint is called the vertex. So in other words, if I start with this initial side and I rotate it, right, that rotation is what forms the angle. The angle is the shape formed between rotating the initial side to this terminal position. Okay, and now we call this point, that endpoint where the initial side and terminal side meet, that's the vertex. Okay, so our convention for angles is that we call positive angles, or I should say, we call counterclockwise rotation positive. So our angles are positive when we're rotating counterclockwise. And that's just because it aligns with the way we draw graphs. If we start in the positive x-axis, then when we draw an angle upward, we are naturally going counterclockwise. So since starting from the positive side of a graph and drawing upward is counterclockwise, we call that a positive angle, as opposed to drawing downward would be a negative angle. Okay, so clockwise rotation is a negative angle, counterclockwise rotation is a positive angle. So the standard position for an angle is with the initial side on the positive x-axis and the vertex at the origin of the Cartesian plane. So if you imagine you're standing at the center point of your x and y axis, and you take your arm and you rotate it upwards, right? That's the terminal side of your angle. The initial side is just pointing straight ahead. Okay, so one more definition here. Two angles are called coterminal if they have the same initial and terminal sides. So, in other words, if I rotate counterclockwise from this purple to blue ray, we'll call this alpha. And if I start from this purple ray and rotate clockwise, we'll call that angle beta. They still have the same initial and terminal sides, even though the angles are different, but we call those two angles coterminal. Okay, and this is should just be a refresher. So we call any angles between 0 and 90 degrees acute angles. We call a 90-degree angle a right angle. We call angles between 90 degrees and 180 degrees obtuse angles. And we call angles that are equal to 180 degrees straight angles. All right, and so one last bit of notations / definitions. So oftentimes when talking about navigation, we divide degrees up into subunits called minutes and seconds. So 1 minute, which is notated 1 with the little dash that looks like an apostrophe, 1 minute is equal to 1 degree divided by 60. So 1/60th of a degree. So almost as if 1 degree is an hour, right? 1 minute is 1/60th of that. And 1 second, which has like the two little apostrophe marks, that's 1/60th of a minute. That makes sense. Which therefore makes it 1 over 3600 degrees. So another way to think of this is 1 degree is equal to 60 minutes, which is equal to 3600 seconds. Okay, so with those preliminary things out of the way, let's go ahead and start just doing a few basic problems. So first we'll talk about drawing an angle in standard position. So 120 degrees. So if I'm drawing an angle in standard position, let's say here's my Cartesian plane, I'll draw the angle part in blue. So in standard position means the initial side is just moving along the x-axis. And we'll draw the terminal side in orange. So I go 120 degrees. One way to think of that, all right, a straight line is 180 degrees. 120 is 2/3 of that. So I'm going about 2/3. So that's 120 degrees. Okay, now example 2, convert the angle to decimal degree notation. So we're given this in decimal minute notation, 45 degrees and 45 minutes. So when we do this, it helps if we first rewrite this and think of this as 45 degrees plus 45 minutes. And then we can just do the conversion on the minutes portion. So how do I convert? Well, all unit conversions are always done the same way. We just multiply by the number 1 in a clever way. The trick is to multiply by the unit 1 in a way that cancels out whatever unit we want to get rid of, in this case minutes, and leaves behind the unit we want. Okay, so how can we do that? Well, if 60 minutes is 1 degree, then what do I know? I know that 1 degree divided by 60 minutes is 1. So that's what I'm going to do. I'm just going to multiply by 1 degree divided by 60 minutes. That will cancel my minutes and leave me with just the units for degrees. So this becomes 45 degrees plus 45 over 60 degrees. That's 45 degrees plus 0.75 degrees. And now, of course, I can recombine this and just write it as 45.75 degrees. Okay. So let's go ahead and move on to another definition. A central angle is an angle with its vertex at the center of a circle. So that's a pretty straightforward definition. So if we've got, if we place the vertex at the center of a circle and we draw an angle from that center of the circle, we just call that a central angle for the circle. All right, so definition, the radian measure of theta is given by theta equals s divided by r radians. Now this is the real important one. So basically most of what we're going to be focusing on moving forward is this idea of radian measure. So of course we're very used to the idea of degree measure, but degree measure is pretty arbitrary. So basically there is kind of close to 360 days in a year, and the Earth goes around the sun over the course of 1 year, so why not divide up the angles of a circle into 360 degrees? So, of course, that's not actually how many days are in a year. And also, it doesn't really do anything useful for us mathematically. 360 is kind of an odd number to pick to divide up the angles of a circle. So instead, what we've done is redefined how we measure angles in a way that gives us more information, in particular about the circles that those angles intercept. So what do I mean there? So what this definition says, the radian measure of theta is given by theta equals s divided by r radians. What we're saying is the angle is the ratio of the length of this side to r. It's asking how many times does the radius fit inside that arc. So whatever your angle is, it's going to intercept an arc on the circle. How many times does your radius fit inside it? That's what this says. That's the measure of the angle. So in other words, if I have let's say a circle like this, and here's my radius, and I draw something roughly like this. Okay, so what I've drawn here, let's say if you took this radius and you laid it along the edge of the circle, this is about 1 length of the radius, this is about 2. So what we would say is theta is 2 here, because theta is the ratio. How many times does the radius fit along the edge of the circle? Right? So that's really useful because it tells us something immediate about the geometry we're dealing with. And since we deal with circles all the time in practical applications, think, for example, how far is your car traveling if your wheel is turning a certain number of times, right? That's how the odometer works on your car. It knows, here's the radius of the wheel, here's the number of times the wheel has rotated, and it can use that to determine the distance by relating that all back to the length along the arc of the wheel. And that all comes from defining our angles in terms of the relationship between the arc length and the radius. So, with that being said, this does lead us to a key fact, a very simple reformulation of this definition of theta equals s divided by r radians. If we just multiply r across, we get that arc length can always be found by multiplying the radius by theta. So, if I know my angle in theta, I can just multiply it by the length of the radius, and then I know how far that wheel has actually traveled when it turned that angle. Okay, so with this definition in mind, what does that tell us about our basic angles in terms of radians? How do they relate to degrees? Well, we know the circumference of a circle is 2 pi times the radius. So this means that a full circle, according to this definition, has radian measure 2 pi r divided by r, right? So just think about the circle. You're taking the whole length along the edge is 2 pi r, and you're dividing that length by r. And that's going to be equal to 360 degrees. That's that's theta in radians, is 2 pi r divided by r by definition. And 360 degrees is also how we define a full circle. So r over r cancels. That gives us 2 pi radians equals 360 degrees. And so that means 180 degrees is the same thing as pi radians. In other words, pi is the straight angle. When I draw a straight angle, that is pi radians. And that's going to be the way that's really useful to think about a radian measure in terms of pi being the straight angle. If we think about that, it becomes actually really easy to figure out what all of our other angles are in terms of radians, but we'll deal with that a little bit later when we touch on some examples. Or, well, momentarily, I should say. So, key fact, if you're trying to convert between degrees and radians, you just do that by multiplying by 1. So I would multiply by either 180 degrees divided by pi radians, or I would multiply by pi radians divided by 180 degrees. And we do those conversions just like anything else. Okay, so now how do we start picturing and drawing radian measure? And that's going to be really important. So looking forward a little bit, we're going to start using radian measure all the time. And it's going to be really crucial in the subject of calculus because radian measure gives us that relationship between the length of the radius and the length of the arc along the circle. And we don't get that relationship with degrees. So since we get that relationship, it allows us to derive a bunch of mathematical facts that only work when we're dealing with radian measure. That means it's really important that we become comfortable using radians and picturing radian angles without having to rely on wasting a lot of time going back to degrees and thinking about degrees or trying to convert to degrees. So how do we start building that idea? Well, all right, I'm going to start by just drawing my XY plane. This says draw the angle 2 pi thirds radians in standard position. So the way you should be thinking of this is 2/3 of pi. So all you got to do is start by taking your straight angle, pi, and maybe it would help you if we delete the y-axis at first, but you should be able to draw this even with the y-axis in place. It shouldn't cause you any problems. And we think, okay, this straight angle is pi, so let's divide it into thirds, right? And just draw roughly some dotted lines to give you 3/3 cut out of pi. And the angle should be 2/3 of pi. So when I actually draw my angle, I always draw my initial side to the right. And I go 1, 2, that's 2/3 of pi. And that's all there is to drawing radian measure. As long as you just think of these as fractions of pi, it's actually really, really simple to draw them. And in my opinion, it's actually much easier because we have a lot of extra thought process we have to go through for degrees. If I try to figure out how do I draw 225 degrees, that's actually a more complicated thought process than just dealing with something like a simple fraction of pi in terms of radians. Okay, so now let's look at a slightly more complicated question. Draw the angle -15/4 pi radians in standard position. So I'm still thinking of this as -15/4 of pi, but it's a little bit harder here because this number is bigger than 1, right? So I have to do a little conversion here. So what I'm going to do is first think of how I can split off this -15/4 into a whole number. So the first thing I think is, what's the largest number less than or equal to 15 that's divisible by 4? Well, it's 12. So I'm just going to split this up into -12/4 minus 3/4. It's the same thing. Haven't changed anything, but it gave me the little benefit of now I have -3 minus 3/4, right? So I'm just thinking of how do I split up that fraction a little bit. So now that allows me to rewrite my angle. So instead of -15/4 pi, I'm going to think this is -3 pi minus 3/4 of pi. And now once I've split up my fraction, this becomes really simple to draw. I'm going to draw my whole x and y axis here this time. So when you're building up this understanding of these angles and this visualization, we want to really make sure that we've got a systematic way to draw them. So when I draw these angles, the first thing I'm going to do, I'm always going to draw my initial side, of course. And now I've got the multiples of pi, -3 multiples of pi. Negative means I'm going clockwise. So each pi, which is half of a circle, right? I'm going to just put a little mark to keep track. So that's 1 pi, that's -2 pi, that's -3 pi. So now I've gone -3 pi, and I need a -3/4 of pi. So now I'm going to divide up the next pi into 4 pieces and go 1, 2, 3. That's another -3/4 of pi. And now I draw my terminal side. So this angle is -15/4 of pi. All right, that's it for that example. Now we will move on to just doing a couple quick conversion problems here. So first, convert 120 degrees to radian measure. Well, I want to cancel degrees, and I know that 180 degrees equals pi radians. So I'll put 180 degrees on the bottom, put pi radians on top. I'm really just multiplying by the number 1 here. So now my degrees will cancel. 120 over 180 is 2/3. So this becomes 2/3 of pi radians. Okay, now we've got to convert negative pi over 5 radians to degree measure. So this time I want to cancel radians, so I'll put my pi radians in the denominator, and I'll put my 180 degrees in the numerator. So my pi over pi cancels and gives me 1. Radians over radians cancels. And so this becomes negative 180 degrees divided by 5, which is negative 36 degrees. So that's it. All conversions in mathematics are always just some clever way of multiplying by 1 so that you cancel out your old unit and you get left with your new unit. Okay, so let's move on to this example. Example number 7, find the missing quantity. The radius here is equal to 0.8 meters. Theta is equal to 342 degrees. What is S? So, okay, we want to find S, and we know from earlier that S is the angle theta times the radius. But this is really crucially important. This is in radians. This formula only makes sense in radians because this formula comes directly from the definition of radian measure. Theta in radians equals S divided by R, and then we multiply the R across and get S equals R theta. But if theta is in degrees, this doesn't make any sense because degrees isn't defined as a relationship between these ratios. So you can never use degrees when you're trying to solve these types of problems where you're relating arc length and radius. And that's one of the most common mistakes that I see students make on this material. So, since that's the case, what do we have to do? The first thing we have to do is convert our angle theta, into radians. I'm trying to make up words. Thadians, that's a new one. So I'll multiply by pi radians over 180 degrees. Now, for now, I'll just leave this in exact form. 342 pi radians over 180. We obviously canceled our unit of degrees here. And so now, applying this formula, we get S equals 342 pi over 180 times a radius, which is 0.8. But keeping with the fact that I've got some nice fractions here, instead of writing 0.8, I'll write this as 8/10 or 4/5. So then I'll multiply this by 4/5. Now 342 is not divisible by 5, so I can't simplify that at all. But 180 is divisible by 4. So before I go to start, plugging the rest of this into a calculator, I can just simplify 180 over 4, or I should say 4 over 180 into 1 over 45. So this is 342 times pi over 45 times 5, which is 225. So this would be the exact answer. Now, if a question asked you to round this in your calculator, what would we get? 342 times pi divided by 225, which is approximately 4.78 meters. Okay, so again, to tie this back to like the real world, what does this tell us here? If I say I had a cart, or let's say a cart with very large wheels, because these would be pretty large wheels, with wheels that were 4/5 of a meter in terms of their radius, and that cart, the wheel rotated 342 degrees as it moved, that rotation would cause this wheel to move 4.78 meters along the ground, because that's the length along the arc of the wheel associated with that rotation. All right, so what's another thing that radian measure can do for us in terms of beneficial applications when we're thinking about angles? Well, it's also useful when we talk about the area of a sector of a circle. This is handy if you want to quantify exactly how much pizza your friend stole from you. Not that that's relevant here. So notice that the area of a sector divided by the area of a circle is equal to the length of the intercepted arc divided by the circumference of the circle. So that seems like a weird thing to say, but it's actually very simple. What we're saying is, if I look at like, half of the circle, the area of a half circle is half, and so is the circumference, or the length along the edge, right? The length of this arc is half of the circumference, just like the area is half of the area of the circle. That's all this says here. Whatever portion of the circle the sector is by area, that's the same portion you're going to get for the length of the intercepted arc, as compared to the circumference. So therefore, if we just take those facts and we put them into formula, if we label the area of a sector A, we get A divided by pi r squared, the area of the full circle, equals r times theta, that's the length of our intercepted arc, divided by the circumference of the circle, which is 2 pi r. So of course, we can cancel r divided by r and multiply pi r squared across, right? So first, let's just multiply the pi r squared across. We get area equals pi r squared times r theta divided by 2 pi r. And so when we simplify this, r divided by r cancels, pi over pi cancels. We get left with r squared times theta divided by 2. So this gives us a simple formula for the area of just a portion of the circle, one sector. So let's take a look at this example. Find the missing quantity where r is equal to 1.25 feet, theta is 45 degrees, and the area is what? So again, theta was given in degrees, but since we are using the length of the intercepted arc, we're using radian measure here, we have to make sure we convert to radians first. So I'll multiply by pi radians divided by 180 degrees. Degrees cancel. 45 over 180 is 1/4. So this becomes pi over 4 radians. So my area is my radius squared, 1.25 squared, times pi over 4 divided by 2. And we'll kind of rewrite this one step at a time. 1.25 squared, so 1.5625 times pi over 4. And instead of writing this as divided by 2, I'll write it as times 1/2. So this is 1.5625 pi over 8. And that's an exact answer, but of course, I might want to write it all as a single decimal. So I'll just multiply by pi, divide by 8, and we get approximately 0.6136. And our units were feet. So this would be feet squared. Okay, so that's it for that one. So we're going to tackle a few more definitions here real quick. First, two positive angles are complementary if the sum of their measures is 90 degrees, or in other words, the sum of their measures is pi over 2 radians. And definition, two positive angles are supplementary if the sum of their measures is 180 degrees, or pi radians. Sorry if you're hearing my dog in the background of this recording. I'm sure somebody is delivering something at the moment, and he just can't handle that. I'm going to wait just a moment. Okay, I think he's done now. Excellent. Okay, so this first picture illustrates the first definition. If you've got alpha and beta, and you add them together and they equal 90 degrees, we call them complementary. And if you've got alpha and beta, and you add them together and you get 180 degrees, we call those supplementary. Okay, and so here's another big idea. So we'll just hit this one kind of quickly. Linear and angular speed. So that sometimes these are made to be a little more complex than they actually are. So average linear speed just means how fast is somebody traveling if they're moving on the edge here. But when we talk about speed, that's just distance divided by time. So when I talk about average linear speed on the circle, right? I'm just saying how big is the arc divided by the amount of time it took to move along that. That's average linear speed. Average angular speed, which we denote with this omega here, equals theta over t. That's just asking, hey, how big was the angle you rotated through divided by time? Right? Distance divided by time, angle divided by time. So linear speed is distance divided by time, angular speed is the angle divided by time. So notice in both of these equations, what do we get? So I get first t equals theta divided by omega if I divide omega across and multiply the t across. And so if I substitute that value of t into the average linear speed formula, I get that the linear speed equals the arc length divided by theta divided by omega. But division by a fraction is multiplication by the reciprocal. So velocity equals omega times s divided by theta. In other words, the linear speed is the angular speed times the arc length divided by the angle. But s divided by theta is the radius, right? Your arc length divided by theta is the radius. That just comes from your radian definition. So that gives us that the linear speed is related to the angular speed as just the product of the radius times the angular speed. So, in other words, angular or linear velocity equals the radius times the angular velocity. Or linear speed equals the radius times the angular speed. All right, that's it. So you might occasionally see some problems with these formulas, but these formulas are pretty simple. So to cut on time, I'm not going to do any particular examples with these. Just be aware that they can come up. Okay, so now we're going to take a look at kind of classical application problem for these sorts of angle measures and relationships. So city A at latitude 33 degrees and 22 minutes is due north of city B at latitude 27 degrees and 35 minutes. Find the distance between the two cities. Use 3,960 miles as the radius of the Earth. So we're going to draw a picture, and that's going to help us make a lot more sense of this. So you've got the Earth, and here's the center of the Earth. And latitude tells us what the angle from the equator is. So when I talk about city A, Actually, let's do city B first, since that's the smaller angle. So city B here, that means that the angle from the equator to city B is 27 degrees and 35 minutes. And city C, or city A, I mean, I'm getting my cities all confused. City A, that angle with the equator is 33 degrees and 22 minutes. So what do we want? Well, the question is asking for the distance between the two cities, but of course we can only travel along the edge of the planet here, so it's asking for the length of the arc between the two cities. And so if we want to know the length of the arc between the two cities, we actually need to know what this angle theta is between our two other angles. But of course, the angle theta here is just take the big angle and subtract the small angle away, and what you get left with is the thing in between, theta. So in order to calculate theta, I need to first subtract these two angles. So we take 33 degrees, 22 minutes, and we're going to subtract 27 degrees and 35 minutes. Okay, so now here's a careful sticking point. So really, really common place to get hung up on here. So when we talk about subtracting these, we have to do something we do all the time when we subtract numbers, which is borrow, right? Problem is when we think about subtraction of, let's say, 25 minus 17, this 20 here is actually two groups of 10, right? So when I borrow, I'm adding 10 to the 5 here, right? I'm taking 10 out of this group and moving it over here. But when I talk about degrees and minutes, degrees is 60 minutes. So here when I borrow 1 degree, I'm adding 60 minutes. So now I can subtract these. 82 minutes minus 35 minutes. That's going to be 47 minutes. 32 degrees minus 27 degrees is 5 degrees. But of course, I'm going to need to convert this into radian measure in order to find this arc length. So that does make things a little bit trickier, but that's okay. So first thing we're going to do to convert this is write 5 degrees plus 47 minutes. We're first going to put it in decimal degree notation. And then once we have decimal degree notation, then we can convert it to radian measure after that. So we got a couple little steps in between here. So 47 minutes here. So we want to convert this, so we're going to multiply by 1 degree divided by 60 minutes. And so what does that give me? This gives me roughly, I should say, approximately 5 plus 0.7333 degrees. So of course I could just write that as 5.783 degrees, and I'll just round down to 5.783. That's close enough. Okay, now I need to convert this to radian measure. So now we're finally going to write theta in radian measure. So that's 5.783 degrees times pi radians divided by 180 degrees. Of course, our degrees will cancel, and we'll be left with radian measure. I'm going to go ahead and do all of this multiplication in the calculator now. 5.783 times pi divided by 180, and we get approximately 0.101 radians. Okay, so now that I have my radian measure, I can use my identity that my arc length is just theta times the radius. So this is approximately 0.101 times the radius, which is 3,960 miles. Which is approximately 399.96 miles. I think it would be safe to round that to 400 if you wanted. Okay, so that's one of the important tools that we have available once we use this Radian relationship that allows us to relate the arc length to our radius of our circles. Now, on a bit of a historical note, this approach was used to measure the circumference of the Earth a couple thousand years ago. So the ancient Greek mathematician Eratosthenes was able to calculate the circumference of the Earth to surprising accuracy, and he basically did the process we did before with a little extra step because he had to figure out what the angle was between two cities. So what he did was he hired somebody to walk directly north between Syene and Alexandria. Those cities are almost spot on directly north of one another, and this was known at the time. And when they did that walk, they were able to measure that they were about 500 miles apart. Of course, they weren't using miles at the time. We're converting to modern measurements. Now, what he did was at the same time, so at the point at which the sun is highest in the day, so at noon in both cities, they looked at sundials, and they knew that at that time, there would be no shadow cast by the sundial in Syene, and the shadow that was cast at that time was 7.2 degrees. So what that showed, because we can basically consider the rays of light from the sun, by the time they get to Earth, they're essentially moving parallel to one another. So we can consider these two rays of light as being parallel. So the shadow cast here is going to be the same angle that gets formed here, because these are opposite angles across parallel transverse lines. So, given that he knew the relationship between arc length, angles, and the radius, he was able to do that conversion. He was able to take that relationship and compute that the circumference of the Earth was roughly 25,000 miles. And our current measurements, that are a bit more accurate than the tools he had available, give us 24,901 miles. So yeah, he was very, very close in his accuracy. Okay, so that's it for this video. Thank you for sticking around.